Okay. All right. So we will continue from yesterday. Huh? Okay. So for today, we will focus more on um, okay, so for today we will focus more on presenting. Okay. Okay, I hope you can see my slides, okay? So today we will focus more on MOSFET and analyze MOSFET bias circuit. Okay. So just a little bit quick recap from yesterday's class. Yeah. So these are the differences between FET and BJT. Okay. Okay. So these are the differences between FET and BJT. I think. Right. So BJT, first of all, yeah, BJT is a current control, current control device, and for FET, yeah, it is a voltage control device. Okay, so that is the main differences between FET and BJT, and both of them can be used for amplifiers, switches, and also impedance switching circuits. Yeah. All right. So this is yesterday's. So these are the types of FETs. Yeah. And in this class, in this course, we will focus more on MOSFET. MOSFET, okay, which is all the example usually is in N channel, right? Okay, so today we will continue look at the one more thing about MOSFET that you need to know is you need to memorize this equation. Okay, so this equation is very important for MOSFET. Okay. Okay. All right. And yeah, so from this equation, you can find K. Yeah, you can find K, and K can be found through this graph, yeah, or which is known as transfer curves, or characteristic graph. Yeah. Okay, and these are the graphs. So these are the graphs. So please note that MOSFET, these are the threshold voltage. Yeah, so the threshold voltage is the voltage that turn on the MOSFET. Okay. All right. So these curves come from this equation. Okay, and from these transconductance or transfer curves, you can also draw a load line. Okay, so usually there is a load line here, and the cross section between load line and this transfer curves, it is known as Q point. Yeah, it's known as Q point. Macam-macam nama ada. Okay. All right. So these are the specifications sheet, okay, for MOSFET that you can find when you buy a MOSFET. Okay, so today we will continue for DC DC analysis, yeah, FET's biasing. So just a little bit recap, yeah, the purpose of biasing is to select proper DC gate to source voltage to establish a desired value of drain current. Okay, so for FETs, we want to find a desired value for a drain current and a proper Q point. So that's why we we do a biasing, yeah, for FETs. Yeah. So there are three types of bias for FETs. This is general FETs. Yeah, FETs. Yeah. So it covers also for JFETs and for JFETs type. Okay. So there are three types, which is self-bias, which is the most common most common bias. Okay, voltage divider bias, and then current source bias, right? And there are three ways to bias a MOSFET. Okay, so for a MOSFET, there are three ways for you to bias a MOSFET. Okay, so there are zero bias. Okay, there are zero bias, and then voltage divider bias, and then drain feedback bias. So zero bias, okay, can only be applicable for the MOSFET. Okay, this is only applicable for the MOSFET, but for e-MOSFET it cannot be used, yeah, because for e-MOSFET the VGS, yeah, the VGS should be larger than the threshold for in order to turn on the MOSFET. So that's why zero bias cannot be used, yeah. uh, so another bias that can be used for MOSFET on e-MOSFET is only these two here, between voltage divider bias and drain feedback bias. But for your exam, okay, we will focus more on voltage divider bias. Okay, so but there are also a few examples for drain feedback bias, but drain feedback bias will not come in your exam. Okay. Okay. So between voltage divider bias, yeah, both voltage divider bias and drain feedback bias, both of them, okay, both of this bias agreement, the purpose is to make, yeah, these two will make the gate voltage more positive than the source voltage, okay, in order to fulfill that VGS should be greater. Okay, so between these two bias, yeah, both of them will make sure that VGS is greater, okay, where the gate voltage, gate potential is bigger, okay, compared to the source potential, right? So DC analysis for FET biasing. So general relationship that you need to know. This is applicable for all FETs, yeah, which is including MOSFET as well. Okay, when IG is approximately to 0 amps. Okay, the voltage at the gates usually, sorry, not the voltage, the currents at the gates usually approximately 0 amps. Yeah, and when the gate voltage currents is 0 amps, okay, the drain currents will equals with the source current. So remember, right? This is for example for an channel, right? So this is gate, this is drain. Sorry, this is drain, and this is source. This is drain and this is source. So you should, when IG is equals to 0 amps, when IG is currents at the gate is 0 amps, so the currents at drain, and will equal current with source. Yeah. So for enhancement types of MOSFET, same as previously, this formula is applicable. It's very important. Okay, so VGS is voltage potential at gate and source, minus VTH is referring to the threshold voltage. Yeah, threshold voltage. And then ID is referring to the drain current. Okay, drain current. Okay, K is always constant. Okay, so no matter when VGS is no matter what condition it is, K is always constant. Okay, even at VGS equals even the VGS value is different. Okay, and ID value is different. K is always constant. Okay, so these are just for your knowledge, okay? But since that drain feedback biasing circuit will not come up in your exam, okay? So this is just for your knowledge for you to know before we go to the voltage divider bias, yeah? So drain feedback biasing circuit. All right. So drain feedback biasing circuit. So these are the example of the these are the example of the circuits. Yeah, so this is they are using the MOSFET. Yeah, MOSFET, and since that the arrow is facing towards the gate, so this is the N channel type MOSFET. Okay, so they ask you find the IDQ, which is drain at the Q point, VGS potential gate source at Q point, and VDS, which is a potential drain source at Q point. So there are two methods that can be used, yeah? Either graphical method or mathematical method. Okay, so mathematical is calculation method, graphical methods is based on graph. Okay, all right. So first of all, in order for you to solve this kind of circuit, okay, we need to remove the resistor RG, resistor here, and also the capacitor here. Okay, so this is same as BJT. Okay, we need to short circuit the resistor. Okay, so this resistor, which we need to short circuit it, and this capacitor we need to remove. Yeah, we need to open this capacitor, so it will leaves only this part. Okay, since that we short circuit this resistor and we open this to capacitor, it will be the circuit gonna be like this. Okay, so this is the simplified version of this circuit. Okay, so from this circuit, okay, you can see that the gate current and the drain current is connected. Okay, is connected. So when IG is equals to 0 amps, therefore VRG, okay, VRG this here equals to 0 volts. That's why we can short circuit this resistor. Okay, because when IG is 0 amps, okay, gate at this current at this gate is 0 ampere. So the voltage here is also 0 volts. So it means that this resistor is not working. So we can short circuit this resistor. Okay, so therefore VDS, yeah, V at DS, yeah, VDS, drain and source is equals with VGS, potential at gate and source. Okay, so which makes, and this will makes, yeah, VGS equals to the potentials at GS equals to VDD. Okay, the source voltage minus with the potential drop at this resistor, okay, which is ID RD, okay, which is the voltage or potential drop at this resistor. Okay, so it will you can get the value of potential between gate and source. Right, next, okay, these are the methods if you want to solve this kind of circuit. using graphical methods. Okay, so by using graphical methods, okay, first of all, we need to plot. Okay, so first of all, plot the line using VGS equals to VDD. All right, at ID equals to 0. Okay, at this point, okay, VGS is equal to VDD. So you will get the x-axis intercept. Yeah, yeah. And then ID, okay, at y-intercept, which is at this y-axis intercept, okay, it is VDD, which is at when VGS is equals to 0. So when VGS is equals to 0, ID is equals to VDD over RD. Okay. Okay, when this VGS, yeah, when this VGS is equals to 0, which is this equation, okay, when VGS is equals to 0, VDD, 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 okay, will be equals to ID RD. ID RD. So for you to find the value of ID, so VDD over RD, right? So VDD over RD, yeah, when VGS is equals to 0. So once you get these two, intercept, yeah, y-intercept and x-intercept connected together. So these are the load line. Okay, this is the load line. Okay, so plot the transfer curve using VGS TH, which is threshold voltage. Okay, ID is equals to 0. Okay, so usually threshold voltage is given. Okay, so you know where to start the threshold voltage. Okay, so this can be plotted using this equation. Okay, this can be plotted using this equation. Okay, by changing the value of VGS, okay, you can find the value of ID. So take several points and then connect the dots. Yeah, then you can get the transfer curves. Yeah, and then you can see that the cross section here. So the cross section here, we're gonna be Q point, the Q point for this circuit. So using the value of ID at the Q point, solve the other variables in the bias circuit. Okay, so from here you can find the value for the other variables or the other values for this circuit. All right. Okay, so these are the methods. Okay, these are the steps if you want to use graphical methods. Okay, usually graphical methods, no matter for drain feedback biasing or voltage divider biasing circuit, the graphical method is always the simplest methods. Yeah, the graphical is always the simplest method compared to the mathematical methods. But it depends. Sometimes some of the questions ask you to use specific methods. It's already mentioned to use specific methods, then you have to use that method. But if they didn't mention to use specific methods, okay, usually we are preferring the graphical methods because graphical method is much more easier compared to the mathematical methods. And let's look for the mathematical methods for drain feedback biasing circuit. Okay, for mathematical methods, first of all, we need to, same with BJT, okay, same with BJT, we need to analyze the input loop. Okay, we need to analyze where is the input loop, first of all. Okay, so if we look at this circuit, okay, so this is the VG, right? This is the VG, this is VD, this is VDD, okay, this is positive minus, and then this is positive, current comes here positive, currents come towards here positive, currents come out through the source, so it's gonna be negatives. Yeah, so the VDS is here and VGS is here. Okay, so let's look at the input loop. So input loop, okay, input loop is at this point, yeah, at this point. Okay, so it will be based on the voltage Kirchhoff law. Okay, VG, okay, minus with VGS, which is the gate and source voltage. Yeah, VG, because just now VG is positive, right? VG is positive, right? Okay, so minus with VGS, minus with uh, VRS, yeah. VRS is here. Oh, sorry, VDS is actually, yeah. Sorry. This is VDS. There's no RS. Okay, so this is VDS. VG minus VGS minus VDS, yeah. So equals to 0. So this is one equation, right? So from here, okay, from here, there is another equation, VGS, ID, and RS, which is at this point. Okay, at this point. Okay, at this point. Okay, at this point. So VGS is equals to VG minus ID, current step flow here. Okay, times with RS, which is the potential drop at the resistor of RS. Yeah, and then. Okay, and then insert the equation of VGS into the Shockley's equation. Okay, so this is the Shockley's equation that we have learned yesterday. Okay, VGS, yeah, into this equation, and then you can solve the ID and VGS. Okay, so if VGS larger than VGS threshold, that is the Q point. Okay, the value from here, yeah, you can find the value of VGS. So if this VGS is bigger, larger, greater than VGS threshold, that is the Q point for the graph, yeah, for the circuit. So that is going to be VGSQ. So that value for VGS is going to be VGSQ and IDQ. So use the IDQ from calculation to calculate the VDSQ. Okay, so let's look at example. So these are the example for drain feedback biasing circuits, okay, where you need to determine the IDQ, currents at drain at the Q point, and voltage at D, which is voltage at this point. Okay, voltage at this point. This is VD, yeah, VD. This is VG, and this is VS. Okay, so what they ask, currents at drain when at the Q point, and VDSQ is voltage drain source voltage here, yeah, voltage between here, drain and source at Q point. So it's given to you the ID. So it's given to you the currents, okay, the currents drain to turn on the MOSFET is at 6 milliamps, okay, and then 6 milliamps. VGS on, okay, is 8 volts, okay, and the threshold voltage is at 3 volts, okay. So first of all, okay, so this is by using the graphical methods. Yeah. So first of all, we need to find the value of K. Okay. So first of all, we need to find the value of. We need to find the value. Okay, we need to find the value of K. Okay, so this is from the equation that we learned from yesterday, from the yesterday's graph here. It's given to you the ID on, and it's given to you the VGS on. It's given to you also the threshold voltage. So from these three informations given, you can find the value of K constants. Yeah. So the value of K constants is 0.24 milliamps over voltage square. Okay, so this value of K is always same for every conditions. Yeah, it's constant. So for VGS at 6 volts, for this, yeah, at this voltage. Sorry. For VGS at 6 volts, which is between 3 and 8, between these two voltage, okay, they choose one voltage which is between these two voltage. Okay, so so it's choosing 6 volts. So for VGS equals to 6 volts, okay, you can find the value of ID. Okay, value of ID. So the value of ID using this equation again, okay, using this equation again, okay, the value of ID is 2.16 milliamps. Okay, so you can plot one plot here, okay, which is when VGS equals to 6 volts. And then another plot here when VGS is equals to 8 volts, okay, which is given to you. All right, which is 6 milliamps, right? Okay, so another point, this only when this 2 point is not enough, okay, this 2 point is not enough, what we need to do is we need to find another point. So for this example, we choose another point which is slightly greater than threshold and also slightly greater than given to you, which is 8 volts just now, right? So we choose another one which is 10 volts. Okay, 10 volts. So using again this equation, we can find the value of ID, which is given 11.76 milliamps. So with this three value, we can connect it. Oh, actually not 3. We have another one value for threshold value, right? So with this 4 value, we can connect this line, okay, and we can draw the transfer curves. Okay, so if you want to use graphical method, first of all, we need to draw the transfer curves. Yeah, without transfer curve, we cannot draw or we cannot solve this equation. Okay, you need for graphical. Yeah, you need to do two. You need to have um, two lines. Two graph, which is one is transfer curve, another one is load line. Okay, which is to find the Q point, load line. Okay, so first of all, after you draw the transfer curves, okay, we need to draw the load line. Okay, so to draw the load line, okay, so this is to draw the load line. Okay, so to draw the load line, okay, first of all, we need to find the 2 points here, yeah, when VGS is equals to 0 and also when ID is equals to 0. Okay, so when VGS is equals to 0, it is always, yeah, VDD over RD. Okay, VDD over RD. Since that there is no current here. Okay, when VGS is equals to 0, so it means that there is no potential drops here. Okay, so it means that VDD VG is 0 and it will be VDD is equals to this is VDD. Yeah? VDD is equals to the potential drop for this resistor. So it means that this voltage divided with this resistor value will give the value of drain currents. Yeah. So when VGS is equals to 0, VDD over RD, so it will give you 6 milliamps. Okay, so that is the Y intersection for Y axis. One intersection for Y axis, yeah, Y intercept. Another intercept that you need to find is X intercept. So this is when ID is equals to 0, right? When ID is equals to 0. So when ID is equals to 0, VGS is equals to VDD. Okay, VGS, when this value is equals to 0, it means that VGS is equals to VDD. It means that there is no VGS is equals to VDD because there is no current here. Yeah, there is no current here. There is no current flow here. Okay, so all the potential from the electric source will flow to VGS here. So VGS will equals to VDD. So it will be 12 volts. Yeah. So once you get these 2 points, you can connect this line. So this will be the load line. Okay, this is going to be the load line, and this is the transfer curves line. Okay. Transfer curves line. Yeah. So you can find there is a cross section between these two lines. Yeah, between these two lines. So this is the Q point. Okay, so this is the Q point. So since that the question asks you to find the ID at the Q point and also VGS at the Q point, so find the value. Okay, the value at this Q point. Okay, the voltage value will gonna be the VGS at the Q point, which is 6.4, and the IDQ, which is the drain current at the Q point, is 2.75. Okay. All right. So this is how we solve this circuit using graphical methods. Yeah. Okay, so since that VDSQ is equals to VGSQ, okay, at the Q point, so it means that VDSQ is also 6.4 volts. Yeah, at Q point, when VGSQ at Q point, okay, VDSQ value will be same as VGSQ. Okay, at this Q point. Okay, which is this is the optimum value for the E MOSFET to work, yeah, to operate. Yeah. So next, let's focus more on voltage divider biasing circuit. Okay, where this circuit will come out in your exam. Okay, so these are the example of voltage divider biasing circuit. Okay, so you can see there's a resistor R1, R2, RD, and RS. So this is same with BJT. If you still remember, bipolar junction transistor, the circuit for voltage divider same. Yeah. Okay. The only difference is they are using different transistor. For this one is they are using E MOSFET. For BJT, they're going to use BJT lah. Yeah. So again, for you to solve this voltage divider biasing circuit, we need to plot the line and the transfer curve to find the Q point. Okay, so it is very important for us to plot the load line and also the transfer curves to find, because we need to find the Q point. Okay, so using the following equation, okay, for the following equation, we will get that the potential at gate here is equals to R2 VDD over R1 plus R2. Okay, why it is like this? Same with BJT. Okay, same with BJT. It is same with BJT. You can redraw again this circuit. You need to redraw. It will be like this, right? It will be VDD, and then this is R1. This is R1. This is R1, and then this is R2, and this is VG. Okay, this is VG. So VG potential drop, VG voltage, since that it is horizontal with this R2. Okay, so the value, since that it is horizontal, so the value of voltage at VR2 is equals to value at VG here. Okay, so then you can solve this using Kirchhoff's law. Okay, you will get these equations. Yeah. Again, next, the input loop. Okay, so this is the input loop. So the input loop is VGS. Yeah, VGS here equals to VG minus minus IDRS. So this is the input loop for here. Okay, ID, RS. So this is positive, this is minus. All right. So VG is positive and VGS is actually minus here, since but they rearrange again the Kirchhoff law. Okay, the formal equation will be like this. Vg equals Vg minus, sorry, Vg minus VDS 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 Allah VDS minus ID R R RS here. Okay, ID RS here. Okay, okay. So if you rearrange this, okay, this is the input loop. Okay, rearrange this, you will get VGS is equals to VG minus IDRS, and the output loop, output loop is at this part. Okay, the output loop is at this part. So VDS is equals to VDD minus ID plus RD and RS. Okay, so the current at drain is same with current at flow at the source. Okay, so that's why ID since that this two resistor is in series, ID is RS plus RD. Okay, so this is two equation that important for this voltage divider biasing circuit. All right, so let's look for same as apa tu just now, same as drain feedback. Okay, voltage divider also can be solved using two methods, which is graphical methods or calculations method, okay, or mathematical methods. So for in order for you for us, yeah, to solve using the graphical methods, first of all we need to plot the line using VGS equals to VG. All right, at ID equals to 0. Okay, so this is very important because this is to find the load line. Okay, this is to find the y-intercept, and this is to find the x-intercept. Yeah, so plot the line using when ID is equals to 0 and VGS equals to 0, and then so once after you do this, you will get the load line. Okay, load line, and then next we need to draw the transfer curves. So first, in order for you to draw the transfer curves, we need to find the K constant first. Yeah, so K constant can be solved using the ID on the value of just now. Yeah, the formula just now. ID on equals to VGS on minus VGS at threshold square. Is 2. Yeah, usually this value is given. If it is not given, then the K value is given to you. So either one is going to be given to you. Yeah. All right, next, plot the transfer curves. Okay, so plot the transfer curves. Once you get these two graphs, okay, find the Q point. Okay, find the Q point, and then using the value of ID at the Q point, solve the other variables that is required inside the bias circuit. All right, so for calculation methods, first of all, we need to analyze the input loop just now. Okay, the input loop. Okay. And this input loop, which is just now, I showed you just now, right? And then insert the equation into the shortlist equation. So this is the shortlist equation. Okay, so this equation insert inside here. Okay, to find the value of ID. Okay, so you have to rearrange. When you insert this equation inside here, you have to rearrange and you will get ID. Usually we will get the value of ID is 2 value. Okay. Since we have a square here, right? So you will get 2 value of ID. So you have to choose either one. Okay, we're gonna look later on for example later. Okay, and then solve for the ID and VGS. Then if VGS is bigger or greater than threshold voltage, that is the Q point for VGSQ and IDQ. And then use the IDQ from calculation to calculate the VDSQ. So VDSQ can be solved using the IDQ. Okay, once you have using the IDQ, you will get VDSQ. Okay, VDD will not have VDDQ because VDD is source, yeah, it cannot be changed, yeah. And RS and RD also cannot be changed, yeah. Right. So these are the summary. These are the what summary, yeah, for enhancement MOSFET voltage divider bias that you need to memorize. Yeah, this is when you are using for the calculation method or mathematical method. This is when you are using the graphical methods. Okay, now let's look at the example. Example 3 for fixed bias MOSFET. Okay, refer to the fixed bias amplifier circuit shown, and then the MOSFET parameters are given to you. So this K value, K constant value is given to you, and the threshold value is given 3.5. And it's mentioned that you have to use the graphical approach. So you can't use calculation approach or mathematical approach. You need to use graphical approach as it is mentioned to you in sub equations. Yeah, and you have to find the IDQ and then VGSQ and VDSQ. All right, so this is given to you. Yeah, 20 volts at the VDD, the source voltage, and resistor RD 3.3 kilo ohms. So this is the E-MOSFET N channel because the arrow is facing towards the gate. Yeah. So this is gate, this is drain, and this is source, right? And at the gate here, there is a resistor, which is 10 mega ohms, and then another 6 volts voltage here is applied to this gate here, right? So first of all, what you need to do for this to solve it, we have to remove all capacitors and draw the DC equivalent circuit. So this is since that there is no capacitors, okay, so nothing to remove, yeah. But if there is, but you need to remove all the capacitors and you need to draw the DC equivalent circuit, yeah. And then step 2, what we need to do is we need to find the value because we need to draw the transfer curves, yeah. We need to draw the transfer curves since that the K value is given, okay. So we can find the variety, okay, some values of VGS, okay, and we can find the value of ID. So VGS value start with above 3.5 volts, okay. So VGS value, yeah, you need to choose the value above than 3.5 volts because lower than 3.5 volts, the MOSFET is going to be 0 volts for the drain value because the MOSFET is turned on when the voltage value of VGS 3.5 above. Okay, so 3.5 you don't have to calculate anymore when the since that this is the threshold voltage that turning on the MOSFET. So the ID will be the 0 amperes, yeah, 0 milliamps. Okay, so in this case, yeah, it's chosen one increment, okay, one voltage increment, 3.5, 4.5, 5.5, 6.5, 7.5. Okay, so using this equation, you can find the drain voltage. Okay, so once you get the value of drain voltage here, you can plot the transfer curves. Yeah, transfer curves. Next, what you need to do is we need to find the Q. We need to find the Q point. So since that, in order to find the Q point, we need to find the DC load line. Okay, so step 3. Okay, GS loop using the Kirchhoff voltage law. Okay, so using the Kirchhoff voltage law, like this, yeah, gate and source, since that there is another source voltage at this point, so we need to considering this this source of voltage too. So we need to use the Kirchhoff voltage law. So 6, let's say we are using this loop here. This is positive, this is negative. So voltage here positive, voltage here negative, and VGS here is negative. So here is VGS here. All right, so 6 minus IGR1, which is here, yeah, IG, the gate current seen flow towards this at this resistor as well. So minus IGR1. Why is minus? Because current come out at minus here, right? Minus IGR1 minus VGS. Okay, minus VGS here. Okay, potential drops here. Okay, so approximation, since that we know the IG is equals to 0. Okay, IG is equals to 0. So we can assume that this resistor is actually will not working here. So since that IG is equals to 0, so it will be VGS is equals to 6 volts. Okay, so in this case, yeah, when there is another voltage source at gate, okay, you can see that the load line is a straight line. Okay, it is no longer slanting. Okay, it is no longer slanting or intersect between y and x axis. Okay, because of why? Because there is another source voltage here, right? So load line going to be straight line. Okay, so the DC load line is a straight line. So since that you get already the DC load line, and there's a transfer curves here, so there will be a cross sectional at this point. So this value will be the IDQ. Okay, IDQ, which is look at this graph, it is around 1.6 milliamps, and VGSQ is here at this point also, which is 6 volts. Okay, and then since that the question asks to find the VDSQ as well, okay, VDSQ as well, so it is different between feedback bias just now, where VGSQ is equals to VDSQ for voltage divider. Yes, IG always approximate 0. Okay. Because earlier I said already mentioned, right? In this one. Okay. IG is equals, we need to assume that IG is equals to 0 amps. Approximate. It is actually not exact 0 amps, but it is so small, we can say that it is 0. Okay. Okay, so now, okay, here. All right. So for us to find the VDSQ, okay, VDSQ. All right. So using this equation, just now, where equation just now? Okay. Using this equation, okay, in order to find VDSQ, we need to use the value of drain current at Q point as well. Okay. Note that, yeah. Note that. In order to find VDSQ, we need also to use the current at drain at Q point, right? You cannot use current at drain other points, yeah? Don't use other points of current, other value of currents at drain, okay? Because actually there is a lot of value of drain current, right? Because you have plotting this, right? But since that is mentioned, you need to find the VDSQ at Q point, so you need to find using the current value at Q point, right? So in order to find, calculate VDS using the DS loop, okay? Using the DS loop. So DS loop is here, okay? Drain source at this loop. So you will get the value is, since the ID is calculated just now from, not calculated, you can find from the graph, okay? So you can find the value of VDSQ, which is around 70.2 volts, okay? 70.2 volts, okay? So now you already solved the questions, okay, using the graphical methods. Okay, so let's look how to solve the same question but using the calculation method, okay? But even though the question asks using the graphical, okay, in this case, even though it's mentioned using the Mana just now? Just now I wrongly show. This one. This is for this is for the, the answer for this now. Yeah, VDSQ is 14.8. Okay, VDSQ is 14.8. So this one, for this example, since that it doesn't mention, okay, this is fixed bias with source resistor. Okay, with source resistor, you can see there is another resistor at the source here, and yeah, there's still another voltage at the gates here. Okay, so, and this question didn't mention that you need to use by doing the DC analysis determine the operating point. It already mentioned, sorry, it's already mentioned graphical approach, but in this example, I showed to you two types of calculation between calculation methods and also graphical methods. Okay, I'm going to look at that. For this question, maybe you can try to solve using calculation method as well, because this is very simple. Okay, so let's look into this question. Okay, where it's given to you, the K value is this value, and the VGS threshold is 3.5 volts. Yeah. Okay, so first of all, we need to remove all capacitors, but since there is no capacitors here, so kita tak perlu nak remove apa-apa pun. You don't have to remove anything. Yeah. And then step 2. Okay, step 2. But if in exam the circuit sometimes is going to be very complicated. So when you see all those complicated circuit, don't get dizzy, jangan pening, jangan gelabah. What you have to do is you just have to remove all the capacitors, yeah, and draw the circuit. It will be like this, right? So that is always the first step. Okay. All right, step 2 is you need to draw the transfer curves, yeah, since that is already given to you the K value, okay, and since that we know the threshold is 3.5, so you need to find another GS value, the drain current with another GS value which is above than 3.5 volts, yeah. So 3.5 volts, we find one increment, okay. Usually we try to find several points of value for VGS, okay. And then using this equation, you can get the drain currents, yeah, drain currents. And then using this drain currents, okay, using this point, we can plot the transfer curves. So settle with transfer curves. We need to proceed again with the DC load line here. Okay, so for you to draw the DC load line, we need to look at this GS, okay, at this loop, okay, GS loop always, yeah, for voltage divider bias, always in order to draw the DC load line, we need to look at this loop, okay, look at this loop. So GS loop using the Kirchhoff voltage law, okay, so 2 minus IGR1. I think this is not 2. Sorry. This should be 6 here. Okay, should be 6. It's a typo error. Please change here. This is not 2. This is 6. Sorry. Okay, so 6. Right. 6 minus 6 volts here, minus potential drop at this resistor, okay, and then minus VGS, which is at this point, yeah, at this point, okay, at this point, okay, at GS at this point, and then minus with this potential drop at RS, okay, RS, okay, IS, but then IS current that flow here is same with current that flow from the drain here, all right? So we can write, instead of write IS, it is also can be written as ID, okay, ID. Okay, so why ID is equals to IS, as I mentioned earlier in this slides, the earlier slides here, okay, when ID is equals to 0 amps, ID is always equals to IS, yeah. And that is solution 4, right? Solution 4, okay. So this one, yeah. So rearrange this equation. You will get VGS is equals to 6 minus IDRS. Okay, so IDRS, fine when ID is equals to 0. Okay, so we need to find the since that we need to draw the load line. Yeah, when ID is equals to 0. Okay, so you just place here, yeah, 0. So it means that when this is 0, VGS is equals to 6. Okay, when ID is equals to 0. Okay, once there is only one point here. Another point is when VGS is equals to 0. So when VGS is equals to 0, the value of ID, rearrange it again, 0. This is going to be minus, not minus, yeah. Bring this to here. Wait, I need to write now. Okay, so here when VGS is equals to 0, right? So ID RS is equals ID RS is equals to 6, right? So ID is equals to 6 divided with the value of RS. How many? 680 ohm. Okay, so 6 divided with 680 ohm. Okay, so you will get the value at this point. Okay, we will get this value at this point, and then connected these two line, so you will get the Q point. Okay, so this is the value of IDQ. Okay, IDQ, and this is the value of VG. Susahnya nak tak? VGSQ. Okay, VGSQ here. And then once you get those, yeah, once you get those two values, okay, you need to find the DS. Okay, since the question asks, yeah, VDSQ as well. Okay, the question asks VDSQ as well. So, okay, in order to find the VDSQ, we need to use the DS loop. Okay, DS loop is here. Okay, it is not loop sangatlah pun, it doesn't look like a loop, but it is here lah, yeah. VDD minus IDRD minus IDRS. Okay, alright, so you will get the value is 17.2. Okay, so this is the graphical methods. Okay, so you can see that graphical methods is very simple. Okay, very simple. Okay, especially when the K is given to you, or even if the K is not given to you, lagilah mudah. It's going to be very much easier. Okay. So quite tricky is the calculation methods. Yeah. So equation A and equation B. First of all, using the Kirchhoff voltage loop. Okay. Okay, we need to find using this loop. Okay, using this loop, okay, we need to find the value of so VGS equals to minus 6, which is 6 here, and then ID R1 here, yeah, which is 680 here. Okay, 680. Okay, so this is actually comes from this loop. Yeah, it actually comes from this loop. Kenapa? Why it doesn't consider this resistor? Why it doesn't consider this resistor at this loop? Because we assume that same as this. Yeah, same as this. We assume that ID is equals to 0. So it's given to you this equation. Okay, it's given to you this equation. Same as just now. Yeah, same from here. Okay, and then another thing. We need to use the Shockley's also Shockley's equation from this equation. Okay, Shockley's equation where K is given to you and GS is not given to you. Threshold value is given to you. Okay, so this comes here, and then once you have these two equation, okay, what you need to do is, okay, by not plotting the graph, what you need to do is you need to substitute A, okay, in B actually. Sorry, this is not C. Okay, substitute A and B. Contoh mata ni. This is B. Okay, substitute A in B. Okay, this ID kan, ID you put inside here, then you will get this ID. It will look like this, right? And you have to rearrange. You rearrange, it will look like this. So you will have quadratic equation. Okay, you will have quadratic equation. Okay, so you need to find you need to factorize this equation. Okay, so this factorization can be solved using calculator. Okay, so because the value is too big, right? And so you can solve using calculator. I hope you know how to solve this factorization using calculator. Okay, and then you will get two values of D. Okay, two value of currents, right? Because there is square here, right? So you, of course, you will get two value of currents. So from these two value, okay, from these two value, take both, find the value of VGS. Okay, take both, find the value of VGS using equation, this equation, Shockley's equation, the V equation here. Okay, and then you will get one value is minus, yeah, VGS1 for this value. Okay, the value of VGS is minus 7.124 volts. And VGS2, the value of the value for ID2, yeah, the value for VGS is 5.52 volts. Okay, since that we know, it's mentioned here. Okay, since that it's mentioned, if VGS is bigger or greater than VGS threshold, that is the Q point. Okay, that is the Q point. Okay, so from these two value, which value should you choose for your Q point? You should choose 5.52. Why? Because it is greater, it is bigger compared to the threshold value. Okay, so these are the VGSQ value. Okay, so the Q point is VGSQ is equals to VGS2, this value, which is 5.52, and the value of I is equals to 0.7 milliamps. So you can see when you are using graphical methods and also the calculation methods, both will give you the same answer. Okay, 0.7 milliamps, 0.7 milliamps, 5.5, 5.5. Okay, maybe the decimals, maybe there is a quite difference between at the decimals, but it will not far difference, yeah, between the calculation method and the graphical methods. Yeah, so if you have time in exam, maybe you can check your answer, yeah, using other methods as well. Okay, if the question asks you to use graphical methods, maybe you can check your answer using the calculation methods. Yeah, so if the question asks you to use the calculation method, maybe you can check your answer using the graphical methods, because those two methods will give you the same answer. All right, like this. All right. So let's look another example. Okay, so we're going to look lots of example. Okay, so this is another example. Fixed bias with source resistor. Okay, so at this point, okay, at this circuit, you can see that there is another capacitor. Okay, it's included at the source here. Okay, so for the biasing circuit shown using graphical approach. Okay, so it's mentioned you have to use using graphical approach. Determine the value of drain at Q point, the value of potential drop at gate and source at Q point, and the potential drop at drain and source at Q point. And it's given the value of K is 0.556 milliamps over voltage square, and the threshold voltage is 3 volts. Then sketch. Yeah, so in this question, they ask you to sketch the ID and VDS characteristics. Yeah. So first of all, the first step, remove all capacitors. So just remove these capacitors. Yeah, these capacitors just as to make the circuit looks complicated, but it is not considered, or it is not calculated inside this circuits. Yeah. So when you remove this capacitor, okay, so it will leave behind only this part. Okay, it will leave behind only this part. Okay, and then step 2, we proceed with step 2. Draw the transfer curves. graph. Yeah. So since that the K is given and then the threshold value is 3 volts, so you need to choose the value of VGS above 3 volts. Yeah. So 4, 5, 6, 7, take several values, and then you can find the value of drain currents, and then you will plot the graph. Okay. So from here, okay, proceed with the DC load line. Okay. So in order to find the DC load line, we need to look at this loop, yeah, VGS loop. So this VGS loop, okay, this VGS loop, there is 12 volts here. Okay, so 12 volts, yeah, and then minus the potential drops at here. Okay, potential drop at here, and then minus VGS here, minus VGS value here, and then minus the potential drops at this resistor. And then since that this IG is always equals to 0, okay, so we assume that there is no resistor here. Okay, this resistor can be short. And IS is equals to ID. So VGS, we're going to leave behind VGS 12 minus ID RSB. Okay. So since that this is a short circuit, right? So these 2 volts can be neglect. Yeah. And then from here, you can find the DC load line by assume that VGS equals to 0 and ID is equals to 0. So you will get two intersect, yeah, two intersection, and then cross both intersection. Okay, so we're at the cross point between the DC load line and transfer curve, that will be the Q point. Okay, that will be the Q point. So you will get straight away the VGSQ, which is 6.5 volts, and also IDQ, which is 7.2 milliamps. Yeah, 7.2 milliamps. And then the question asks you to find as well VDSQ. Okay, VDSQ. So VDSQ, to solve VDSQ, we need to look at this loop. Yeah, this loop. So VDD minus VDSQ minus RD, minus potential drop at this point, and also minus the potential drop at this point, RS as well. Yeah. So you will get so this 12 and this 12, yeah, take into account. Yeah, you have to take into account for the calculations. So it will be VDSQ equals to 5.5 volts. Yeah, 5.5 volts. And then, so these are the relation. Yeah, these are the sketch the ID and then VDS. So VDS 5.5. So since that I think this question is not finished yet. Since that they ask you to sketch, yeah, ID and VDS characteristic. So once you get the ID and VDS, how to find? You have to change the value of ID. Okay, change the value of ID using this graph. Yeah, okay, change the value of ID using this graph, 2.25, and then you will get the different value of VDS, and then plot the graph. Okay, plot the graph. If the graph looks, okay, based on the sketch graph, if the graph look like this, so it means that this circuit can be used as amplifier. So it means that it's amplify the currents, yeah, the drain voltage is amplified at the output. Yeah? But if you see that it is decreasing, so it cannot be used as an amplifier. So you can see the relation between VDS, okay, ID and VDS characteristic to say either the graph, either the circuit can be used as amplifier or not. All right. So we can see here the effect of this resistor RS. So what are the effects of the source resistor RS? So the source resistor RS helps to stabilize the Q point. Yeah, usually the resistor RS helps to stabilize the Q point because without the resistor RS here, you can see that the Q point It's like this. The Q point. The DC load line, we're going to look like this. Okay, but with the existence or with the existence of this resistor at the source, you will get the DC load line. It will look like this. Okay, so this will make the Q point stable. Yeah? If the gate bias increase, the source current will increase, but not as much as when there is no source resistance. Yeah. So if the gate bias increase, the current at the gate increase, of course the source current will increase as well, but this will not be as much as when there is no resistor. Yeah. So that's why the function of this resistor Rs helps to stabilize the Q point, and this will later affect the AC again. Okay, so this the existence of this resistor later on, will affect the AC. We will look later when AC after this. Maybe next week. We will look into AC source. Up until here, we are discussing the DC part only. Okay, later on, there will be AC source here. So this will affect, and therefore the source resistance is necessary to stabilize the Q point. Okay, so it is essential to have this Q point, this resistor, and please memorize as well. This might be asked during your final exam. Okay, this is the hint I give to you. Please remember the function of this source resistor as well. Okay, because this question might be asked during your final exam or during your test later on. Okay. All right, so let's look another example. Okay, so this is the voltage divider bias with the single supply. Okay, single supply, only VDD here. Okay, figure as below shows a common source CS MOSFET voltage divider bias amplifier circuit, and given the parameter for MOSFET is threshold is 2 volts, 2 volts, and the value of K constant is this value. Then determine the Q point as VGSQ and IDQ using the graphical approach. Then calculate the VDSQ. Right. So the answer is this. And this is the answer. Okay, so let's solve these questions. Yeah. Okay, so we are using the graphical to solve the VGSQ and the IDQ approach. So first of all, what you need to do is we need to remove the capacitor. Okay, so just remove this capacitor. Okay, this unnecessary, just remove this capacitor to make the circuit look simplified. Okay, so the circuit we're going to look like this. Okay, still remember about Thevenin, so we need to use Thevenin as well. Okay, so R1 and R2. Okay, find the total resistance, and then also we need to find the Thevenin voltage. So it will look like this. Yeah, it will look like this. So the Thevenin voltage will be 4.65 volts. Yeah, so it will be like this. So this is the Thevenin voltage as well. Yeah. Okay. So and then RS, this RS. Okay, same, and then RD. All right. So this is the circuit. We're gonna look like this after you simplify the circuit, right? And then find the Thevenin. Okay, so this is find the Thevenin. So this is same as previous. Yeah. Find the voltage Thevenin and then the R Thevenin, resistor Thevenin. So these are the value. Okay, and then step 3, find the JS loop. JS loop here. Look here. The JS loop here. Yeah. So when you have this circuit, you don't have to look back into here anymore. Okay, so JS is here at this. Yeah. So JS here will be VG. So there's VG here. Then apa tu? IG, RTH, R Thevenin here, and then VGS. VGS is VGS at this point. IDRS at this point. Okay, so the approximation is IT is equals to 0. Okay, IT is equals to 0, and then VG here is referring to here. Okay, jangan I think it's quite confusing because you might confuse with the VG here at this point, right? But VG here is actually this VG here. Okay, VG yang kat sini. Okay, V Thevenin. Okay, I think it's better to write V Thevenin here so that it will not be confusing. Okay, so mana? Okay, D tukar pada TH ya. TH, okay. So and then you will get this, yeah, VGS is equal to this value, and then from this value we can draw the DC load line. Okay, draw the DC load line by IT is equals to 0 and VGS is equals to 0. Okay, and then so this you will get the DC load line then, yeah, and then draw the transfer curves. So it's up to you. Either you want to start with the transfer curves or you want to start with the DC load line. It's up to you. Which one did you prefer? Okay. So in this case, before we start with the transfer curves, right? But in this case, we start with the DC load line. So it's up actually. It doesn't matter with what kind of graph that you want to find first. Yeah. Okay. So from the this shortlist equation, you can find the transfer curves, and then you will get the Q point here. And from this Q point, you will get the IDQ and VGSQ. All right, and then from here, okay, from this IDQ, you can find the VDSQ. Okay, VDSQ using this loop, yeah, VDSQ, where VDD minus with the IDRD minus with IDRS, yeah. Okay, so you will get VDSQ is equals to 5.5 by using the value of currents at Q point 0.7 inside here, right? And then I think it's finished from here, yeah, until here. All right, so graphical, then calculate VDSQ, right? So this is using graphical methods. How if we are using the calculation methods here? Okay, so for if you want to use the calculation methods, so first of all, you need to come up with this VGS with this loop. Okay, you need to come up with this loop first, yeah, where it will gives you VGS is equals to 4.65 minus RS here, yeah, IDRS, and then this is one equation. Another equation is we need to use the shortlist equations, yeah, and then this equation, okay, this equation, equation C put inside equation A, so or equation A put inside equation C, either one. Okay, you will get this, yeah, you will get this equation and rearrange this equation. You will get this quadratic equation, yeah, quadratic equation, and then you have to factorize this equation. Okay, you can factorize this using calculator, okay, to make it faster. Okay, make sure your calculator can factorize this, yeah, because some of the calculator can't, right? So make sure that your calculator can use to factorization as well, okay, during your exam, okay, so that you don't have to use manually. Okay, so you will get the ID2 value, ID1 and ID2. So between these two values, which one that you need to choose for VGSQ? Okay, so in order for you to decide, you need to use this equation again. Okay, equation A. All right, so look at the value of VGS. If the VGS value is greater than VGS threshold, that will be the VGS at Q point. Okay, so in this case, the value of VGS at the Q point is 3.92. Okay, so when you get this value, so you know that the value of IDQ is this 0.73 milliamps. Okay, so by using this IDQ value, then you can solve the solve the VDSQ as same method as this. Okay. So your answer, you can see, your answer is going to be not so far different. 0.73 milliamps using calculation, 0.7 milliamps using graphicals, and the value of VGSQ 3.92 using calculation, 3.9 using graphicals. Okay, so either one is correct. Okay. So example 7. Okay, for today we're going to look lots of example. Example 7. For the biasing circuit should calculate the IDQ, VGSQ, VDSQ, VD, and VS. So for in this question, they ask another value of voltage, which is value at this point, value of voltage at D, and also value of voltage at S. Okay, so from VDS, you can find the value of voltage for at D and value of voltage at S. All right. So same, first of all, calculate the, so in this case, sorry, another thing, in this case, they didn't given to you any constant K value, and they didn't mention either you want to use graphical or calculation. So you can choose either one, yeah. The only information that's given to you is VGS Thevenin, sorry, not Thevenin, VGS threshold is 5 volts, ID on is 3 milliamps, at VGS on equals to 10 volts. So from here information, you can find the K value, right? The K constant value, you will get the value is 0.12 milliamps over volts square. So next, draw the simplified circuit. So this simplified circuit, same, you need to use the Thevenin theorem to make sure that the Thevenin theorem to simplify. Okay, so it will look like this. Okay, this circuit later on we're going to look like this, right? So from here, from here, you can find the not the threshold, the transfer curves, and also the DC load line, right? So the transfer curve using this K that you have calculated just now earlier, okay, and then the DC the VGS, yeah, VGS, choose 5 above, yeah, above than the threshold, okay, because at this one, because if you choose lower than 5 volts, it means that the MOSFET is not turning on yet. Okay, so choose above than threshold, you will get this sort of drain current series, yeah. So you can plot this graph. So the graph is going to look like this, and then based off with the GS loop here, you can find the DC load line. Okay, so you will get the DC load line when this equation. So when ID is equals to 0, find the value of Y intersection, and then when VGS equals to 0, you will get the X intersection, and then the cross section between DC load line and the transfer curves will be the Q point, and the Q point you can straight away you will get the IDQ and VGSQ. Okay, so using this IDQ value, you will get the value of DSQ. Okay, value of DSQ here, right? DSQ using the DS loop, yeah, and then. Okay, the value is 14.06, and then since that the question asks to calculate the VD, value of voltage at D, and value of voltage at S. Okay, so VD is equals to VDD. VD here is equals to VDD, which is 40 volts here, minus with this. Better look here. VDD here minus with this potential drop, so you will get the value of VD here. Right, value of VD here. So so value of ID, since $40, okay, minus value of ID. Let's say that you want to use 6.7. Where did we get 6.7? 6.7 at the Q point here, yeah, 6.7. And then times with the resistor value, you will get the VD value. And then VS is Vs is here, right? Vs is here. So Vs is equals to ID times Rs. Right? Is the Vs here is equals to the value of value of potential at this resistor. Okay, so ID times with the Rs, so you will get the value is 5.494 volts. Okay, so these are the these are the steps. Yeah, when the steps is the same. Okay, the steps is the same. First of all, with the Thevenin, and then find the transfer curves, and then find the DC load line. Okay, using the GS loop, and then using the DS loop, find the VDSQ, and then from that you can find the VD value, VS value. All right. So try to verify this using the mathematical approach. The answer shouldn't be far from this graphical value. Yeah. So let's look another example, okay, which is using dual supply. Okay, dual supply, where there is a 12 volts here and then minus 12 volts here. Okay, and there is a capacitor here. So first of all, remove all this capacitor. Okay, remove all this capacitor. This capacitor remove, and then find the value of constant K. Since that there is no constant K is given to you. Okay, is given to you the VGS on at 6 volt and ID on at 5 milliamps, and the threshold value voltage is 3 volts. So you can find the value of K. Okay, from here, we need to simplify this circuit using Thevenin theorem. Okay, and you will get the R Thevenin and also V Thevenin. Yeah, V Thevenin and R Thevenin, and find the transfer curves. Yeah, transfer curves using the Shockley's theorem. Okay, using this K constants value, right? And then try to find a few of VGS voltage value, and then you will get a few value of current, yeah, drain currents here. And then with this value, plots the transfer curves, yeah, and then proceed with the DC load line. So for DC load line, same, you need to use the GS loop using the Kirchhoff voltage law. So here, yeah. So for here, okay, VG is this value, right? So VG, which is this value 3.84. Why it is minus? Because it's come up through minus here. Okay, because the value here is minus, right? So it's minus. So it will be minus here, minus, and then minus, since that this is IG is 0, so you don't have to bother with this resistor, and then minus with this VGS, yeah, VGS minus with this VGS, and then minus with this IDRS, okay, and then plus with VDD. Why plus? Because when you take this loop, why plus? Because when you draw here, yeah, this come out from minus, right? Minus, positive. So this is minus, so this is positive. You are taking this loop. So you can see that it come out at the positive sign. So that's why it will be plus, yeah. Okay, so that's why it is plus here. Okay, that's why it is plus here. All right. So you using this equation, so find when ID is 0. Okay, what is the value for x-intercept, and then when VGS is 0 for the y-intersection. So you will get this DC load line, and then you will get the Q point, yeah, the cross section, the Q point, and from here, using the currents of the Q point, can find the VDSQ. All right, and then calculate the VD and VS, same as just now. Okay, VD is the potential difference. 12 minus ID RD will be the VD value here. Okay, and then VS is the same with the potential drops at this resistor. Okay, so it will be like this. Okay, using the same currents at the Q point here. Yeah, right. So you will get this value. All right. So try again to use this using the mathematical approach. So these are the summary. Okay. Oh, it's a little bit blurry. Yeah? Okay, these are the summary, okay, for the biasing summary. So this is the feedback configuration. So feedback configuration, you don't have to you don't have to focus much, because in your exam, in your final exam, in your test, they will focus only for this voltage divider. Okay, so practice with the Thevenin. Okay, practice with the Thevenin theorem, and then find with this GS loop, and then VDS loop, and then with this transfer curves and the DC load line. Okay, this can be drawn using Excel. Okay, this can be drawn using Excel. If online, kan? You can draw using Excel as well for this one, right? Okay, kalau graphical lah, graphical. Okay. Okay, so I think that's finished our class today. Any questions about the DC MOSFET, DC FET? Later on, we will proceed with AC. AC will be quite pening sikit lah aku AC. Alright, any questions? Oh, -5. We have 30 minutes extra. I finished earlier today. Itulah. So that's why try, jangan peningkan dulu yang ni, fahamkan dulu DC ni, master DC, then baru boleh pergi proceed with AC. Usually memang AC memang pening. AC is quite complicated. So maybe AC kita boleh recap. For AC BJT pun pening kan, and then AC MOSFET pun mungkin pening. So AC mungkin kita boleh recap during revision later on. Okay. So look again to the example. Nanti later inside your e-learning, I will also put the past year questions. Okay, look at the past year questions. Past year question, I think is helpful sebab most of the lecturer change the value of past year questions. Okay, so past year questions sangat-sangat membantu. So try to solve the past year question as well. Okay, any questions about that? Okay, MOSFET graphical methods. During your exam, contoh matanya, sebab hari tu we already discussed for your final exam. For your final exam, we will focus on graphical method. So calculation method, senang kan? Calculation method will not come up. Yeah, graphical methods. So focus on graphical methods for IDQ, VDSQ. Okay. Alright. Transconduct. Okay. Into this will kind of be in AC. Right. Standby lah. Panel as well. Right. So any questions? If there is no questions, then we can our test one sensei. Yeah, okay, your test one. Dah. I already finished mark. Some of you tak cukup masa, right? They leave blank for attendance. Oh, of course, wait. Okay. For your test one, boleh guna tak yang kecil ni? Try to scan this one. How was it? It's okay, but most of you for question 3 and question 2 tak cukup masa. Okay, and some of you leave it blank. So sometimes don't leave it blank sebab write the equation, because from the equation there will be marks that will be given to you. So don't leave it blanks lah. Okay. Okay, but you did well. Most of you did well for the part 1, part A. So part A, good. But it will cover a little bit lah for the test 2. Test 2 will be estimated next week. We will be the lecturers will discuss about test 2. Test 2 will be somewhere around it, yeah. Kejap test 2 we have been decided to the exact date is not confirmed yet, but it will be around kejap kita dah we know the weeks but we don't have the exact date yet. Okay, so test 2 will be this one. Okay, test 2 will be conducted on test 2 week 11, which is around 23 to 27 May, around next week, around 2 weeks more like that. Okay, but we don't have the exact date yet. We also doesn't have prepared again the question yet. We only prepared your final questions. Final dah prepare tapi test belum prepare. Okay, for mirror during test the mirror is not compulsory yet, but for your final mirror is compulsory. Okay, for test so far the information that I have, mirror is not compulsory yet for test, but for final mirror is compulsory. Okay, so kalau if you can practice mirror during test is better. So you know how to set it up, so you will not pening later on lah for the final. Shopee mirror, okay, belilah. So prepare a mirror, bigger mirror, yeah. Okay, because there is another one student, but for other section lah, they use a very small mirror. So jangan guna small mirror yang guna kat toilet tu. Okay, so prepare mirror besar. Or if you have 2 screen, better lah. Can if you have 2 device, you can have 2 screen, it's better. I think students nowadays have too many device, right? Okay. Alright, so okay, so that's all for today since there is no questions. Okay, so later on we will proceed with the AC, minggu depan we'll proceed with AC. Hope we can test satu markah. Apa tu test satu markah? You want to know your test 1 marks, is it? You want to know your test 1 marks? I can share if you want to know. Yeah, okay, then I will share that. Okay, I will share later on. Alright, so prepare lah to know your test 1 mark. Later on I will share. Okay, so okay, so I hope for today is okay. Tak ada apa-apa lagi dah. We can finish until here. Yeah, okay, so tak ada yang dalam UTM, right? None of you inside the UTM, right? Because I think inside UTM now at the college there's the COVID is very yes, the COVID is very high nowadays, yeah. Some of the college has been tutup dah. So be careful, yeah. Kesian kalau students yang tak boleh nak balik tu. So be careful if you are around UTM, okay, and pray to our Palestinians too. So that's why they already they already decide that your final exam will be online as well. If not, final exam patutnya in class. But since that the cases high, so that's why your final test is online as well. Okay, so let's pray for our friends yang dalam UTM tak boleh nak keluar. We hope the cases drop, okay, and also for the Palestinian country as well. And take care. Selamat Hari Raya. Assalamualaikum. Thank you.